This is 4.3 Logarithmic Functions and Graphs, College Algebra. We're on page 374. So the first couple lessons of Chapter 4 had to do with just getting used to inverses and exponential functions and some of that basic stuff so that we could get into the meat and taters of logarithms starting today. So if you notice, top of page 374 where it says logarithmic functions, it says we have noted that every exponential function where a is bigger than 0 and it's not 1 is 1 to 1. So we're talking about something like that, where a is always bigger than 0, but it's not 1. It can be any number as long as it's not 1 and it's bigger than it's a positive number. Thus a function has an inverse that is a function if we're talking 1 to 1. In this section we will name these inverse functions logarithmic functions. So instead of calling them inverse functions, we're now going to call them logarithmic functions. So if we have something like x equals 2 to the y power, in order to find in order to graph this, all we have to do is plug a number in for x and it'll kick out a y. So we just use our little table there and we plug numbers like 0 in for y and it gives us a 1 for an x. We put a 1 in for y, it gives us a 2 for x. We put a 2 in for y, it gives us a 4 for x. So we can go ahead and put all those together and graph, and we end up with a graph that looks like something along that line. And one thing I wanted you to note in this graph that we had here of y equals 2 to the, or x equals 2 to the y power is notice that it gets close to the y-axis, but it never crosses the y-axis, because if it crossed the y-axis, that means that our x value would be 0. And when we have a function that looks like this, there is nothing that we can put in here for y that's going to give me an x value of 0. So that's why my x value never gets to be 0 and it ends up being on the y-axis. So therefore my y-axis is going to be a vertical asymptote. Alright, so if I were to reflect that across the line y equals x, like that, if I were to reflect that across there, all I'd have to do is change this to y equals 2 to the x power, and then it would give me a graph that looked like this. Okay? Using my x as my asymptote. My x-axis is my vertical asymptote. Alright, so down in the middle of page 375 it says, note too that this curve looks just like the graph y equals 2 to the x power, except that it is reflected across the line y equals x, as we would expect for an inverse, and the inverse is y equals 2 to the x, or the inverse of y equals 2 to the x power is x equals 2 to the y power. And if you remember doing that handy dandy formula that we did in order to change these back and forth, we used that idea of the 4 steps, which are in the middle of page 275 if you want to look at that. So mathematicians have defined a new symbol to replace the words the power to which we raise 2 to get x. Okay, so actually we're taking this equation right here, and what that says is, what power do we have to raise our number 2 to, what power here, in order to get x? Or we could use numbers and say 2 to what power would give me 8. So that's saying I am looking for a number to raise my 2 to in order to get 8. So y would equal 3, because 2 times 2 is 4 times 2 is 8. So 3 would be the number I have to raise 2 to in order to get 8. Okay, and so rather than read that whole thing and say it like that, what power do I need to raise 2 to in order to get 8? They've come up with a new symbol, and that symbol is, and you've seen this before, log, and it is L-O-G. And the way you would write, what exponent do we raise 2 to in order to get 8? We would put our base here, and we would put our x here, and we would put our y here. So this is saying, what number do we raise 2 to in order to get x? So y is the exponent that we're looking for. So when you're writing things in logarithmic form, when you're going back and forth between, this is called exponential form, to logarithmic form, notice the exponent is always by itself. The base is always in the lower part of the log. It's a subscript. And the x, what we're looking for, is always next to the log here. Okay, so it kind of gives you an idea of where all these go. Y goes by itself, 2 is the base, x is right there. Okay, so that's the way you write it in logarithmic form. Okay, so let's look at solving some of these. Okay, so we can look at that, and it makes it a little bit tricky, but if we write it in logarithmic or in exponential form, it makes it a little bit easier, because it says, what number can I put on 10 that would give me 10,000? So 10 times 10 times 10 times, times what would give me 10,000? In this case, 10 to the 4th power. So my answer is actually 4. 4 is the exponent that I need to put on 10. If I had something like log with a base of 10 of 0.01, means what exponent can I put on 10 that will give me 0.01? Okay? So in this case, this 0.01 is the same as 1 over 100. So I'm trying to get 1 over 100. So if I put a 10 to the negative 2, that means I have 1 over 10 squared, which is 1 over 100. So therefore, the answer I'm looking for is negative 2. That's my answer. The log base 10 of 0.01 is negative 2. Okay? If I have something like the log base 2 of 8, means what number can I put on 2 that will give me 8? In this case, it's going to be 3. And so on and so on and so on. If I had something like log 9, that is going to, I'm trying to find out the exponent. So I'm trying to find the exponent that I can put on 9 that's going to give me 3. Well, what relationship do I have between 9 and 3? Well, I know 9 is the square root, and I also know the exponent symbol for square root is 1/2, and that would be equal to 3. So what I was looking for is 1/2 there for this answer. So what exponent can I put on the number to give me what I'm looking for? So what about log with a base of 6 of 1? That means what exponent can I put on 6 that's going to give me 1? Well, you know in your algebra background that if x is ever 0, anything it's attached to as an exponent is going to give you 1. So your answer is just going to be plain old 0. Okay? So, in the middle or page 378 up toward the top, there's a couple rules there that we're going to look at real briefly, and they're just regular old algebraic rules that work with logarithms. that says 1 says if we have the log with a base and there's a 1 there, then that equals 0. So for example, if I put 3 in for a, and I said, okay, what exponent can I put on that to where I'm going to get 0? You can obviously see that, or I'm sorry, not 0, 1. So we took our base, we took our 1, put it here, and we're saying, okay, so what exponent can I put on 3 that will always give me 1? Well, the answer is 0. So log base a of 1 is going to equal 0. Let's keep going. Log base a of a equals 1. So let's write it in exponential form. Let's use a number here. So instead of a, let's use 3 again. So it's saying that my base is a. It's saying that my exponent is 1. And that's going to equal, according to this, it's going to equal my base. And my base is 3. So I'm going to put a 3 here. So 3 to the first power is going to be 3. Okay? So there's 2 rules for you right there that are good to keep in your tool belt for later use. Ends up being very handy. Alright, so one of the things that we're going to do is learn how to go back and forth between exponential form and logarithmic form. So let's go ahead and get started with that. Example 3, we have exponential form. 16 equals 2 to the x power. This is my base, so I'm going to write it as log of 2. And I also know that my answer is going to go here, and my exponent, and my exponent is going to go at the end. So really easy to write. If I have 10 to the minus 3, and I say that equals 0.001, if I want to write it in logarithmic form, I write my base, and I'll write my base as being 10. And by the way, just for your information later on, whenever the base is 10, you don't even have to write it. It's kind of like when you have 1x, you don't write the 1 in front of the x. Well, if there's not a 10, if there's not a number down here, it's assumed that it's a 10. So you don't even have to write it. You could just say, yeah, I just don't even want to put it there. But for right now, let's go ahead and leave it there. And that equals, I'm getting a little bit ahead of myself. 0.001 equals my exponent, which is negative 3. So that's how I would write that. Okay. When I have it the other way around, when I give you your logarithmic form first, so if I were to write log base 2 of 32 equals 5. If I wanted to change that to exponential form, I would write the base, I would write my exponent, and I would write my 32 right there. 2 to the 5th power equals 32. Okay? So, not a whole lot of tricky stuff there. But as far as using your calculator to find logarithms, it all depends on your calculator and what you have. But you should have a key on your calculator that looks like this. Okay, so you've got a log key right there, L-O-G. You're going to use that one. You're going to use this key too later on, but right now you're just looking at your log key. So you should be able to put in whatever log that you're looking for and find the answer by clicking on this. But notice, this log key doesn't have a base, and we have been talking about that. If you have a log that has a base of 2, compared to a log with no base. When it does not have a base, it's an assumed 10. Okay? Which means that this log button only works when we have a base 10. You cannot push this button if the log has a base other than 10, like 2. So later on I'll show you how to convert this 2 to a 10, and it's a pretty easy process. You've all done it before. But this button is only when we have a base that's 10. So because each calculator is a little bit different, I'm going to give you a couple just to practice on. So if I give you the log of 645,778. That says, what exponent am I going to put on 10 that would give me this number right there? Okay? And your answer should be, if you're using your calculator, it should be 5.8101 approximately. So what that means is, if I were to take 10 and put an exponent of this power, which seems weird because you're used to having like 10 squared or 10 cubed, but if I put 10 to the 5.8108 power, I'm going to get this number here. So if I took 10 times itself, 10 times 10 times 10 times 10 times 10, that's 5, times not quite 10 because it's 0.8101, I'm going to get that 645,778. If I were to use log of base 10 of -3, what I'm looking for is 10 to what power gives me a -3. Now when you plug that in, you'll get an error because a logarithm does not exist as a real number, because there's no real number power to which we can raise 10 to get a -3. We cannot raise this, or we cannot have a number there for x that when we take 10 to that power, we're going to get a negative number, or to get a -3. Okay? The number 10 raised to any real number power is got to be a positive number. So, common logarithms of a negative number do not exist as real numbers. And we'll get into some changes and all that later on. All right. And that brings us to natural logarithms, which natural logarithms are really no different than common logarithms, which we've just done. So, a common logarithm would look like this, with the base 10 of, say, 1,000 equals 3. Okay, so 10 cubed equals 1,000. Another way of doing these logarithms is with natural logarithms, and the difference between natural logarithms and common logarithms is that the base is not 10, the base is e. And if you remember, we did we talked about the number e in lesson 4.2, and really all that e is a number, 2.71828, etc., etc., etc. It's kind of like pi. It's a constant, and it always represents that number, but it gets confusing because now there's an extra letter there. But instead of writing the log with a base e of x, what they've done is, for natural logarithm, they just write ln of x. And what that means, ln of x means log with a base e. That's the only difference there. Okay? And if you look at your handy-dandy calculator that we have been looking at, notice what we've got here is an ln key. So this is natural logarithms, and notice, you can't see it very well, but see the e to the x power? So that is your e, and there is your 10 to the x power. See, the 10 is the base, just like your log here has a 10 as a base. Your e here is the base. Your ln has an e as a base. So they match. They have that commonality between them. So let's look at something like ln of 53. That again means log with a base e of 53 equals something. So in exponential form, something is an exponent on e that will give me 53. And that something then is 3.9703. So when you plug ln of 53 in your calculator, you'll get 3.9703 for your exponent that you're going to put on e. Okay? So that is the first video, 4.3a.